Hey guys, this is Roger. We're going to go over the HPLC data analysis right now. So, first of all, where is the data? The data is on Canvas. You can look on the 155 page under Files, then go to Lab, then go to HPLC data. Choose your day, for example, Thursday, and you can download your files from there. Once you have your files, then you should be able to see them in Acrobat, roughly like this. And for example, here is Anthony. This is, I believe, Thursday, and the serial number file name is Tony0001. So Tony did 1 through 5, and then the next one will be identifiable to another person by the name on the upper left of the description. That's the only place that name appears, and then the other descriptions are down below. So, how to get the data out? Well, this run is for standard 1, and standard 1 is 5 parts per million. So it's the low standard. And you see we have 2 chromatograms. In this case, the first chromatogram is recorded at 275 nanometers, the second one at 230 nanometers. Now, you can see that at 275, the peak at 4 minutes is somewhat larger here. It's about 30 versus about 10 or 12 MAU at 275 and at 230 nanometers. This corresponds to a peak in the caffeine spectrum at 275. Right? On the other hand, at 230, the peak at 7 is larger than the corresponding peak at 7 at 275. So what this does is this identifies the 4-minute peak as caffeine and the 7-minute peak as benzoic acid. So what we want to do is we want to record the data here from these chromatograms, and the data appears in a big table down below here, right? Now there's signal 1 here and signal 2 here, so there's 2 tables, right? The first table is for 275 nanometer data, and in this case the only peak that got recorded was the 4-minute peak. Now, for convenience, let's simply take the 4-minute and the 7-minute peak at 230 nanometers, and we will record these data. Okay? So, what we're going to do is we are going to, for this part of for this video, we're going to focus on the 4-minute peak, the caffeine peak. And we're going to look at the area in MAU seconds. Oops, the area here at 4 minutes. So that signal is going to be 169.4 MAU seconds. So MAU seconds is the integral of the peak that is in the chromatogram. So that is going to be the area under this peak using this pink baseline there. The pink baseline was automatically determined. So now let's see how we can do this. So let's go to Excel and let's write down these values. So we're going to need a concentration column here and a signal, and we'll specify 230 nanometers here. And the concentration is going to be 5, 10, and 20 ppm. And at 230, we got 169 MAU seconds. Then If we go to the next chromatogram, we will see for example that, we'll see here that in the second file for Anthony, this is Tony 2, right? We can go, now all 4 peaks are quantified here, but we're going to look at this peak at 230 nanometers. So there's 275, here's 230, here's 4 minutes. The next peak is 328.3. So let's go to that guy. And that is going to be 328.3. Go back there, and then the third one is going to be 637.97 or 638. Nanometers, there we go. So now we're going to need to linest these guys. So let's do highlight a 1, 2, 3, 4, 5 by 2 region. Then we're going to type equals linest, and we'll put in the y's, comma, the x's, comma, go down to true and hit the tab key, the comma, go to true, hit the tab key, close the parens, and then type Shift Control Enter. All right, so here's our linest, and so this parameter on the left is slope, this is intercept, right? And these are the corresponding uncertainties here. So this guy here is SY, right? And I think that's the only important values that we're going to get out of there. So let's go ahead and make predicted Y values for this. Right? So this predicted Y value is going to be equal to M, and we're going to push F4 times, so it's going to be equal to M, push F4 times X plus B, and we'll push F4 on B as well. That simply inserts dollar signs and makes those absolute references. And then, so now we can drag this down to 3, right? Now we can get the predicted values there. So I'm just going to get these sig figs under control here by reducing them there. There we go. And so there's the concentration, the actual signal, the predicted signal, and they differ just very slightly here. So these would overlap on any normal graph. Now what we want to do is we want to get the signals from the Excel data for the samples. So let's go back to Excel. Now we're going to go to the next file over here, which is going to be Anthony 4. You can see here this is Anthony 4. Now this is, here's the true chromatograms again, right? 275 and 230. Now you can see that there's a series of components that show up here at shorter retention time, but that the later retention times where the caffeine and benzoic acid come out are essentially clean. So again, we're going to use 230 nanometers to be consistent with the calibration. We're going to put the caffeine in here, 3.998 is where that came out, and the area is 698.4. So we can go back to here, and we can go 698.4. And then now we're going to go to the next one, which is Anthony 5. There's Tony 5. There we go. 230, 3.997. And that's 448.37. And I just realized I made a mistake here because I took the 270 nanometer for this guy here. I'm going to go back, and I'm going to go up here to Tony 4. There's 275. Oops. Here's, that's Tony 5. Here's Tony 4. Get a little confused here sometimes. So there's 275, and there's 230. And this table is actually split here, 3.998. And the area is 400.1. So it's not 698, it's 400.1 here. Got a red flag there because it came out to be over 20 MAU seconds there. So these are all data here. So let's highlight them in a particular way. We could make them sort of light orange, right? Predictions we can make in say light green, right? And now the prediction that we're going to make here is actually not of signal, but of concentration. So concentration here, we can highlight those cells, we can put it here, and this is going to be equal to y minus b, y minus b, again we're going to have for that, divided by m. For that baby. And there we go. Copy this guy down and get the sig figs under control. There we go. So these are predicted values now. So, so let's just go ahead and start making up a little table here. So we can just take that guy there. Right. So this is the sample concentration. And that is, and it's going to have a plus or minus value here, right? So we'll go to insert symbol. Symbol will be plus or minus. And there we go. Just drag this guy down. And then the uncertainty here is going to be the result of a rather massive equation, right? And if you recall, what we did last time was we got the equation from the lab manual and then copied it in there. This is actually from the other spreadsheets. So, but here's SC, and it's dependent on all these other values, right? So S sub y over absolute value of m times all this stuff, right? So let's just go ahead and set this up, right? All we have to do is this one, right? So we're going to say equals, and I'm going to put in the terms, right? There's one term, the first term, times the square root of the second term, okay? Now, if I go into the second term, I'm going to have, in turn, 1 plus 1 plus third term, right? And then the third term is going to have a numerator, which is squared, and a denominator. I'm going to go ahead and put the denominator in parentheses as well. So let's go ahead and start filling these guys in. This is going to be SY. We're going to F4 that, divided by M. So we'll take the absolute value of M. Doesn't really matter in this case whether you take the absolute value of M or not, because it's positive. And then we're going to take it. Now we're going to do the square root of 1 divided by 1, right? That's because M is the number of replicate measurements we made of Y. And 1 over N is 1 over 3, because there's 3 cal points. And now Y unknown minus average of Y cal. So Y unknown is going to be the signal. We're going to subtract the average of Y cal, right? And then that term is squared. Right? And now the denominator here is going to be equal to M squared, so it'll be this guy here, M squared times SX, or times this term here, which is equal to the dev square of X. Right? So that should work. So I think that worked. It gave me an error. I think it made a correction earlier on, but this is, I'm quite sure this is correct. There's the first term. There's the second term. There's the grouping on the second term. Yep. Yep. Oops. I think we have a mistake here. No? No, we don't. We're good. We're good. Let's see here. Get the numerator here. Yeah, no, we're good. I think we're good here. Yeah, okay, we're good. I'm just checking those parentheses, right? So this I should be able to drag down because everything is F4 that needs to be. Oops. I don't think so. Let's see here. So it is, actually we need to place an F4 on these guys. All right. Dragging this down again. Oops. This didn't work again. So we need to F4 these guys because they don't move either. And then E2, this is M. This has got to be F4'd also. Okay. And then there's M up here, right? This is E2, that needs to be F4'd. So let's see now. There we go. So this is correct now. And I'm going to go home. I'll get these sig figs under control here. So now, actually 2 sig figs is perfect for this. And that means that this guy, actually, we should display 1 more sig fig. So because, oops, 2 more sig figs actually. Because right now 2 sig figs in this means that the thousands place is displayed. So we need the thousands place displayed here. So there we go. There's our uncertainty, right? Now we need to convert that, and this, or the unit of this is ppm, right? And this is injected, right? Now what we need to do is we need to convert this into ppm prepared, right? And so now what I'm going to do is I'm going to make some example masses, you know, and I'm assuming here that you used mass to dilute the samples. And this is where you took a little bit of Diet Coke and then about 10 times as much water and pipetted them into a vial and you weighed them. And so if that wasn't the case, if you did it by volume, you'd use corresponding volumes here. But doesn't really matter. But here it goes. So M1, M2, right? And this is going to be 0.743, for example, and then 7.541. I don't know what you guys used. These are probably values are probably too high. But just to give you an idea, right? And then the S, the uncertainty, these values, we're going to say give them 1 milligram in each case. So here we go. These are both going to be grams, right? So then we're also going to have a volume for the can. And then a T value for let's see, let's try it this way. 95.T.1. Okay. So the volume of the can is going to be 0.355 liters, right? And then the 95% confidence level here is going to be equal to T.INV of 0.95, comma, and the degrees of freedom here is 1 because we have 3 minus 2. It's 3 cal points minus 2 degrees of freedom, 1 for slope, 1 for intercept. So there we go. There's that, 6.31. And we can reduce these guys. This is unitless, right? So now these guys here, just to recall, these are just examples. So I'll highlight them in red there. These are examples only. And then use your data. Oops. Use your data. Okay. So let us figure out how many parts per million we have in the Coke. So we're going to take the sample concentrations and multiply them by the volume ratios there. So what we got here is equals this times this. Oops, wait. Can't do that yet. I got to name these cells here because we're probably going to use them over again. So, formulas, create from selection, left column, it found them, yay. The same thing here, create from selection, left column, yay. Create from selection, left column, yay. Let's see how this one, yeah, 95T1, you can, SM2, SM1, M2, M1. Oops, sorry. I was looking at the wrong values. M1, M2, SM1, SM2, V dot can, and underscore 95T1. Doesn't matter. Okay, so let us say here this is going to be equal to sample concentration times this divided by this. Now, since I gave these fancy names, I don't have to make absolute references there, right? Equals this times this divided by this, right? Now, let us now think about how to set up the uncertainties on these values, right? To account for this dilution, there is a process, right? And basically, to get this, we've got three terms. We've got the value, the mass, and the mass, right? And we need to account for the uncertainty in all three of those. And since they're all multiplied and divided, we simply take their root sum square, their Pythagorean square, and multiply that by the value that we get. So we're going to take this value times. Hey, Raph.
Hi.
How's it going?
I'm good.
Good.
I just checked out yesterday the data that you posted, but
Yes.
our data is not even in Tuesday or Thursday, Wednesday.
I'm sure I saw NAOD in there. I'm sure I saw NAOD. So hold on. Actually, I'm almost done with this. Give me 5 minutes and I'll be in and we'll find it. Sorry, I'm a little behind. No problem. Let's see here. Oops. So I have to erase that part. So let's see here. So now to get the confidence interval, this is standard dev. And this is going to be 95% CI. This is going to be equal to T times S divided by the square root of N, which is 3, right? And I'll get these sig figs under control. Bring that down to 2. This goes up by a substantial factor over the estimated standard dev because there's very few degrees of freedom here. And I'm going to save this now as HPLC Workup. All right. And now the only thing left to do here is to calculate the upper bound. Oops. Upper bound, the lower bound, and then the nominal value, and then the agreement. So the upper bound will equal, well, actually it's going to be, the upper bound will equal that value plus the 95% CI. The lower bound will equal the calculated value minus the 95% CI. The nominal value is 45, and the agreement in this case is good because 45 falls between 45.7 and 43.3. All right, so let's just see these guys. And in this case, there's not agreement there. So, and that is just fine That is all you need to do for caffeine. And then if you do the same thing for benzoic acid, then we are perfectly good. Awesome.